Hello. I haven't streamed in quite a while, about a year. Hey Toby, nice to see you here. So, according to the poll that I ran about an hour ago, it seems like people would like to hear a bit about compilers. So yeah, let's get started. So let's just do a quick search. What is a compiler? Thank you. Is this better now? I will continue talking and let me know. So, looking at what a compiler is. In computing, a compiler is a computer program that translates computer code written in one programming language, a source language, into another language, the target language. Hey, thanks for coming. So basically, if we look at what a compiler is, it's a translator. So it translates code written in one programming language to another, but this kind of translation phase is quite general, and a lot of things can it can be applicable to a bunch of stuff. And if we think about the different stages of compilation, or what a compiler is, if we try to visualize it, we have some source language and we process the text, make sense of it, try to figure out, for example, types and other scoping rules and name resolution, and then we process it. We try to optimize it in some cases. So some compilers do some sort of optimizations and some don't. And then we translate it into some sort of a target code. And it doesn't have to go from like a high level to a low level. It could also go from like C to JavaScript. Or I would say like taking HTML and converting that to PDF is also a compiler. So if we look at this more closely, what are the interesting parts of a compiler? One important part is the parser. So let's write down a few things. Let's call this actually syntax analysis. The idea here is that we take some code, or of course this could be anything, but something along the lines of like ID, x equals x, which means like an identity function, and we make sense of it. Like, we need to figure out the structure and know what the user is trying to say here. And usually the output of a syntax analysis in modern compilers is an AST, which stands for an abstract syntax tree. Computer program can work with text, but it's a bit difficult, especially if you want to do some changes to the program. We kind of need to convert it to some data that has better meaning or is easier to work with. So we take this kind of expression or statement, and we, in Haskell for example, we translate it into an ADT. So if I were to represent this with a data structure, then I would say that this is a definition, and a definition can be can have a name for the definition, and we can say this is some sort of text, and it has parameters in some cases, which can also be some sort of text. And then we have the body, or the depends on the language, could be just an expression. So for example, in C or other imperative languages, this might be a statement, or a list of statements, or even a block with nested scoping. It really depends on the language. With functional languages, usually we like to say that everything is an expression. So we will represent this as some sort of a data type that we will continue to refine. Let me know if it makes sense, and if you have any questions, I'm happy to answer anything. This can be a discussion more than lecture. So moving on, this kind of data type needs to be created in some way. So we need to be able to take some text and create a definition, or even a list of definitions. It really depends on how complex our source language is. Like, this could be in Haskell, this has to be like a module with some sort of a name and maybe an export list and some import statements, and all of these has to be defined in some way in a data type. So if we write this, for example, as our source language, actually, let's go with actually the load, and let's expose ID, for example. So let's try and define some sort of a data type to represent this. So we can say that this is a module, and this module has a name, and let's give it some sort of a text for now, but in Haskell usually this is like this could be, I don't know, data.text. So it's often a good idea to make these types a new type. So this could be like module name, and this could be a variable or name, and parameters could also be a name or just a param. And then we can give new types for these, and later we can further refine them depending on how complex our language becomes. So module name would also be text, for example, and param would also be text for now. And what else? We have an export list. And we have an import list. Or this could be even an import, because this can also become a little bit more complex. And then we can have definitions. And everything here can be needs to be defined in some way. And let's add just one more data type here for the sake of completeness. An expression could be just a variable. And with this, we should be able to represent our program, our target program. We use this entities in Haskell to translate the program above. So this stage right here of taking text, trying to verify or understand the syntax, is called syntax analysis, and in many places this will also be called parsing. So let's just name this. As we take a file, and we or like text in a file, and we return a module. And this is the idea of the first stage of the compilation, is taking some text that represents a program and converting it to data types that a computer can work with. So if we try to represent this program in these data types, it would kind of look like this. We have a module, and maybe I'll even open another scratch. So we can see this side by side. So the name would be module. Oh. Should be module name. This should be name. Should be on. This should be input. Hey! Thanks for coming. We're talking about compilers for a bit, and we are trying to represent the program on the right in data types. So this would be name, and the export list would be name ID. The import list would be import code, and the definition would be have one, and it looks like this. Yeah, so this is the main idea of parsing, and it can be a little bit cumbersome in my experience, but this is like what we have to do to start working with compilers. And let me fix this a little bit. Okay. After we have this kind of data type, and when we start working on compilers and other projects even, my go-to approach is to start with a very simple and minimal bare bone MVP that you want to work with it, and then add features on top of it. So for example, all of this module thing, we don't really have to do it. We don't even have to do this definition thing. We can just start with an expression and work with it. And at least this is my opinion. And this is the approach that works for me. So after we do the syntax analysis and we make sure that we have some sort of data type or data that represents our program, we can start work with it. And there are a bunch of stuff that we can do with it. The next thing is semantic analysis. When syntax talks about the way that the text is written and trying to understand what the user wrote, semantic analysis talks about the meaning of the program. So, for example, it will try to do name resolution. Maybe the program that the user wrote, and let me copy it to the buffer. Let's call this the source program. This is the ST. So now in the semantic analysis stage, what we want to do is to figure out if the program makes sense. For example, if we were to write this program, this would not really make sense because y is not really declared anywhere in the program. So this is the responsibility of the semantic analysis. And the reason that Haskell is effective for writing compilers is exactly this. First of all, we have a very nice way to represent AST. For example, if I wanted to add some sort of another type of an expression, I could use ADTs, some types, to enrich my expression. So I would say add expression, and this is kind of a recursive kind of a tree that we're building here. And now I can write this kind of program and maybe change it to double, I guess. So let's change our program. Yeah. So yeah, as I said, Haskell is pretty powerful in this regard. First, because we can represent syntax trees as ADTs, and this is a little bit more involved in other programming language. For example, if we were to choose an object-oriented programming language, we might have a class for each kind of constructor in the expression, and we might have we would have to and for example, if we were to choose C, which doesn't have ADTs, it has like a it's not like a, we can try to use unions and structs to build something that looks like an ADT, but then we don't really have the constructors which give us the type safety, and we don't have the case analysis. We basically don't have pattern matching. So one thing that another thing that we can do in Haskell is write functions that process a tree. For example, if I wanted to check if let's say I have a list of parameters and I want to verify that any name in the expression is in that parameter list. That would be fairly easy to write with pattern matching. Let's try and do that. So what would be a good name for this? Let's call it scope check. Let's get a list of params, which of course would be better as a set. And we can return a bool, for example. Or better yet, a list of mismatches. So let's have params, and of course we need to check some sort of an expression, right? So let's take an expression and do some the first case that we have is var name, and maybe this would be better as a set of name. And we can check. Hello, welcome. And we're talking about compilers and Haskell. So is this name member of the params. And if it is, then we're basically done. We can return an empty list. And if it isn't, we can return it, and to indicate that we didn't find this in the params list. And the other case we have is add. So add for two expressions, and then we can recursively scope check with each expression. So we can say scope check for expression 1 and scope check for expression 2. And of course we need to fire the params as well. So in a pretty simple function we're able to process trees in Haskell with recursion. And the cool thing about Haskell is that it even lets us skip this process if we use like more advanced libraries. For example, with the Uniplate library, we can skip all of this case analysis and just say give me the names from universe by expression, and I want all of the names, and I want the name to, and I don't even need to write this because it will be inferred, and name is a member of params, or actually not member of param. And this will do the same thing basically. Let's format it a little bit. Hi, thank you for coming. Yeah, it just works. I don't know how it works, but it works. I'm guessing because I have Haskell mode installed and this begin source here does the job. At any case, Uniplate provides us with like generic traversals on data types, and because we define this as a new type, we can try with universe by fetch everything. So why universe by and not just universe? Universe, its type is, if I remember correctly, it's like an on to list of on, meaning that these two types are the same. So if we replace on with expression, which has the type expression, we'll just get all of the expressions. The nice thing about Uniplate is that universe by is that we can choose whatever we want here. This could be anything else. This could be like an A and give me all the B's. So it will find all of the names inside the expression and will give us just the names. Let's make sure that I am correct about this. Universe by. Yeah, so form can be anything and two can be anything, and that can also be a problem sometimes, because at exactly the same way I could write give me all the ints in universe by, and there aren't any ints in my expression, but it would type check still and just won't return anything. So we have to be a little bit safe with it, but And this is like a really cool thing about Uniplate, this flexibility, and Haskell in general, because it provides us with this kind of functionality that we can just write things in a really concise way. So in this stage of the semantic analysis, we do this kind of ideas, and we can also translate our initial AST into something that is a bit more specific or precise. For example, if we have a list of params here, we could maybe that could also, for example, as a user, I could write this kind of text, and this would look in the data type like this. We pass these two params here, but maybe there is a better type to represent this, to make sure that in the syntax, in the semantic analysis part, we will reject this kind of program, and then later on we don't need to check it again. We can convert this into a type that fits better. And for all of the correct programs, it could be like some sort of a set, I guess, but set doesn't have like an ordering, and we need ordering, so maybe not a set, but something. So another cool thing that we usually do in semantic analysis for statically typed programs is type checking. And I have a tutorial about type checking if you're interested. Don't think we can cover this right now. But basically the idea is that we check that the operations that we can run on the expressions is valid. And there is a way to actually run these operations, and they fit, they make sense. So generally we will annotate each node of the expression and definitions with like an additional, for example, type or some sort of annotation. And we say that the type for this is like for all type var a, let's say this is a type constructor of arrow. This is getting a little bit complicated, but bear with me. Type application with, let's top line here, and also here. So this is the first application, and then another O. So let's finish this. So this gives us is this correct? Maybe. This kind of type gives us some sort of a carrying ability, but we could also represent this differently. We could represent this as a type function, as a function that takes arguments, types as arguments, and this could be like a list of parameters, and it returns a parameter. It really depends on the kind of capabilities that our language has. And here also we would annotate the types for each of these. So this variable would be, oh, in this case, this is not ID anymore, right? This should be double, and this shouldn't be an A, this should be a literal. So maybe type int if we have them in our language. And so on. The next big stage is usually, again, it could be optimizations, which can try to do a bunch of stuff to make the program go faster. So, for example, you can try to inline some of the expressions, some of the code that we have, and to avoid indirection or jumping to a different function. It could also do the opposite. It could find some sort of an expensive expression that happens multiple times and try to just compute it once, put it in some sort of a variable, and then reference it again. So there are a bunch of stuff that we can do in optimizations. They are very dependent on the language that we are implementing, just like anything else here. And there are many compilers that don't really have much optimizations. Compilers that have a lot of optimizations are usually called like optimizing compilers. This is a really cool place to explore. There are a lot of development and research specifically on this stage, and all of the stages, but this one in particular. But we are going to skip it a little bit. The next part would be code generation. And again, as we said, our target language, our source program, our source program would be could be anything. Like it could be HTML, it could be JavaScript, it could be make files, it could be anything. And our output, our target code could also be anything, depending on what we want to target. And that could really change the kind of optimizations that we need to do and the kind of features that we need to support. For example, if I am implementing a language like PureScript, implementing it and targeting JavaScript makes it a lot easier because we don't need to support garbage collection, for example, and closures and everything, because JavaScript is a pretty powerful functional language that has first-class functions and everything, and that makes the compilation stage really easy. Hi, hello, welcome. Nice to have you there. So when we're talking about code generation, it really depends on our program and our language. But the idea is, just as we have some sort of pattern matching kind of thing, we can do case analysis and emit code. We take an AST and we convert it to instructions in case we translate it to something like assembly, for example, or just other AST for JavaScript could also be an option. So for example, if we take this example and we take, for example, just our expression, and we'll say, how can we represent this? Or even better, let's take our definition. So let's call it just def. So what would a def look like? We could write JavaScript here, and we can also just write text, right? So this would be some sort of a let, I guess. Let name of the def. Be equals to a function that takes intercalate map emit param params of the def. We can also write this a bit nicer with concat, for example, or even unwords. So basically, compilation is taking a thing from one language and emitting something that represents it in a different language. And the kind of power that we need, the kind of abstractions that we need to implement in like more low-level terms really vary depending on the language. So, for example, in my virtual machine project, I am working on implementing primitives for a type functional language that I can take a programming language like, for example, maybe not Haskell, but maybe something simpler like Gimel, and emit bytecodes that run on this virtual machine that is written in C, and it has most of the mechanism like garbage collection and closures and everything, and that would make my life a bit easier. But for example, if I had to write if I wanted to target Intel assembly, I would also need to include an additional runtime system that would track allocations and do garbage collection, and I would have to figure out like a layout for how to represent data in the runtime system, which I still need to do, but yeah. So this is like a very, very high-level overview of compilers, and the main way I would recommend to learn compilers is do it incrementally and do it across the board. So the way that I usually start writing a compiler, I start with this expression, and I write something that is not too complex, but maybe a bit fairly small, but has enough features that I'm interested in, and I write the code generation straight out of that after that, and then I have some sort of loop where I can write my own programs in an AST and then translate that into some JavaScript, for example, and then I can run this with Node or in the browser or things like that. And After that, I can add more features. For example, here we started with something really simple, but we could make it even more simple. We can have, we didn't have literals, but we could start with just literals, right? Instead of having an expression with names and scope and addition, we could just start with something like a number. And now we would think, how can I translate this to JavaScript, for example, or assembly code? And this would be fairly simple. In JavaScript, if I wanted to print this, I would write for node, for example, just write Haskell here. We take this expression and we turn text. So our expression is a number I, and we can convert this just to the number I, and let's say this is string, and like maybe wrap this around in something that is a program. And what is a program? Program is print expression. So this would be print expression. And this would be emit program. And this could be console.log emit expression e. That's it. Now we can take this tiny little thing and write it in Node. Let's actually do that. Why not? New compiler. Let's take an argument. Okay, so let's jump to here and then do like unghc tiny compiler, and let's pass it 1, 2, 3. Put a match failure in a do block. So let's start with this. Let's even say that parse equals read.head. Let's print the arguments to make sure that I pass them correctly. So let's remove this, and we got our program. So now I can take this and I can pass it to Node.js, and it prints it, does what it's supposed to do. And once I have this very minimal kind of program, I start iterating on it. For example, I can now depends on the kind of language that I have. Maybe let's do something a bit different. Let's do, instead of this print, we'll say that the program is a list of expressions, and we'll emulate some sort of a stack machine. But then I need to include an additional thing, so maybe let's do something else. Thing is, I don't really want to spend too much time parsing, but okay, let's do it. So an expression would be, for example, adding two expressions. And what would be an easy way to parse this? So I could say that my language doesn't have like an explicit add operator, but it can have, if I write multiple numbers, I would expect it to add them all up. So in this case, instead of doing this, I will do this, and then I will fold out, add, and I need to start with something. So let's start with 0 maybe. So what is the type of fold out again? Okay, so I will be starting with so I need here a function that takes some I number and an existing expression and adds them. So I will add E to the number I. So let's even add this below here. This takes a list of strings, and what we want to do is translate this into an expression. Okay, so now I need to remove this, and now we need to take care of this. We need to add something for add. So we could do that. We emit expression E1, and then we add this plus sign and emit expression E2. And I believe that should work. Let's give it a try. Okay. So I hope this is the correct answer, but I believe it is. And this is like a very simple way to get started with programming. Just try creating something that is very, very minimal, and then go over the stages and iterate on it. And there are courses that I can recommend that teach compilers. So let me throw this in the chat. Can I think I can't. Let me write it real quick. Hopefully that would be the correct link. But the idea of what I just showed you is of iterating over building a compiler is actually explained in this paper called an incremental approach to compiler construction by Abdulaziz Gulum. And the idea here is that this is a really neat way to start understanding compilers, and these two courses and this book follow that approach, and I got a lot of mileage from that. I tried quite a few courses and books to learn about compilers, and these are the ones that clicked for me, so I recommend them. This uses two of the first ones use OCaml, but I just translated it to Haskell. It was quite nice, quite easy. The translation, and they define some sort of a basic functional language, and they convert it to x86, and they have notes. This course has notes that describe and explain how to incrementally build a compiler, including function calls and tail calls and a bunch of stuff. And the other course is more of recorded lectures. It really depends on the kind of learning resources that you like and what works for you. So these are like my recommendations. And have a project, do the exercises. It's what worked for me. Yeah, any questions, or anyone wants to ask anything? Another really cool project that I will mention is GBCC, which is one of the poll options that I mentioned that I was interested in reading through the source code of GBCC and see how it works. It specifically works with the incremental approach for compiler construction as well, and this is what drew me into to learn about it. It is it says that so first of all, this is a compiler for the C language, and it's a real enough compiler that real world programs can be compiled with it, including Git, SQLite, libpng, and so on. Regarding dependent types, I am interested in seeing how far we can get with a simpler language. So I feel that Haskell is getting very, very big, very, very complex, and that makes certain kind of stuff harder to work with. For example, tooling and error messages. And my language, I am planning on doing something a bit different and trying to keep it minimal but powerful and see how far it takes me. I haven't really spent a lot of time with dependent types, but I am interested at some point. Another question. I've been seeing posts and more mentions of bidirectional type checking. Do you have thoughts about it? I've implemented Hilde a couple of times, and there are plenty of resources to find a way around to implement other features like extensible records or pattern matching, etc. Not sure it would be that easy with bidirectional type checking. So yeah, that's a really good question. I am also a little bit confused about bidirectional type checking. It seems like it is a very straightforward way to implement a type checker and some type inference, but all of the resources that I ran into leave something to be desired in terms of type inference. So my impression is that if you're going through the bidirectional route, you still need to annotate some of the types, which could be workable for any kind of languages. It really depends on what you want to do. I really want my language to not require any type annotations at all. And the constraint solving approach, which is also, as far as I understand, implemented in Haskell, seems to work quite well with it. And I was able to implement extensible records and pattern matching and even polymorphic variants with this approach, and this is the one that I prefer at the moment for lack of understanding of bidirectional type checking, I guess. So if you're interested, do explore it, but I think it's also fine to just use HM and maybe constraint solving. Your blog, by the way, I recommended it many times. I use it myself a lot. Thank you. I really happy to hear that. Getting feedback is something that is really important to me, and I'm really happy to hear that people find it useful. Thank you. Most of the things that I write is things that I have struggled with, and it took me a lot of time to figure out from different resources, and I try to write to my past self, hoping that if this article was available, I would have an easier time. So I'm trying to make it easier for others if they are similar to me. So yeah, GBCC. GBCC is is able to compile real world programs, but it's still like a toy or more of a learning kind of compiler. It's supposed to be really clear and the code base really clean, and the nice and cool thing about it is that it is written with the incremental approach in mind, so each commit builds up incrementally. So we can start with the first commit and see like how it has like a makefile, and exactly what we said. We have this argument, and this is like the head. Get the first argument, and then we generate assembly with moving this, parsing the ASCII to integer of the first argument, and then returning. And the next commit builds on top of that, and so on. Adds addition and so on. And I am very excited to learn more about compilers and even C programming from this code base, and maybe we'll find the time to stream and look at this together. It is often you find implementation focused PL articles. Your articles are great for engineers more than academics. Thank you. I am not really an academic, so yeah, I'm trying to write something that is more approachable for me. So you prefer type annotations to be optional. Sometimes I wish they were mandatory, especially when writing Scala. So yeah, I think that as a coding convention, it is very important for to annotate types, but it is also very useful to just have the compiler infer it, and I don't want to give up that power because I use it for writing tests, for writing prototypes. This makes Haskell like a very concise language. If I can just emit all of this and just like very quickly write something down, and it works, and that's really cool. And I can use the compiler to generate the type signature for me. So yeah, if I added can I do this? Let's try. Let's add options JC -w. Does that work? Yes. And so I can move the annotations and have this pop up, and then Dante will let me, with a click of a button, just add type annotations, and this is very powerful in my opinion, and something I don't really want to give up. And this is another really cool thing about Haskell. I needed to remember this before to add this add in order for this to work, but now that I added this annotation, and if I even add w error, this would not compile, and I would have to implement this. So yeah, this is kind of checking is very useful because we can just we can have the compiler tell us when we add a new kind of data constructor. Hey, this is the final not used, and this case expression is missing an implementation for mal. Yeah. Type annotations will be optional only for simple code. If code are polymorphic, we need to use type annotations for a specific type. This is, as far as I understand, true for bidirectional type inference, but it is not true for general Haskell code, right? I think you can write things like add xy equals x plus y, and repair using add signature. this is a polymorphic function with a type class annotation, and it is able to infer the type without issues. So this is something that I don't really want to give up, and which is why I am more interested in constraint solving kind of algorithms. Yeah, if you go like more deeper and like you need type families and rank types, then yeah, you probably need to add a few type annotations, but this is like a double-edged sword. Sometimes when you have to add type annotations, maybe that means that your program is a bit too complicated. Maybe you should think about simplifying it so you won't need that. Sure, it really depends on maybe we get great value from type levels things, but this is a point where I would stop and think, do I want to make this trade-off? Sometimes I do, sometimes I don't. And yeah, Hindley-Miller and constraint solving type inference algorithms can calculate and generate general type without type signatures, unless you need more features like very complex type of things. Which is why I like them. Yeah, I don't have a lot of experience with dependent types. I do have an Idris 1 book I bought like years ago, and I haven't read it. I'm not very good with books, but this is on the to-do list. I am interested in exploring this and see if the power to weight ratio is worth it. I'm not sure, and it's worth exploring. Specifically, if you go to my blog and you're interested in constraint solving kind of type inference, I have this article series actually, type inference for Gimel's type inference engine, which is my language, and it goes over my understanding of unification-based constraint solving, and this might be useful for you or interesting for you if you're interested in type inference. And if you don't understand this article, please let me know, and I will try to both explain it to you if you're interested, or try to make it better. And this goes through and talks about extensible records as well, and polymorphic variants, which I implemented in my program language. Hey, what's up? We're talking about compilers. I am actually about to stop in a few minutes, but the recording will be available in my YouTube channel. And does this work? Let me check. I should have commands here. I don't, but my link to my YouTube should be somewhere below here, and my blog is like here. why not as in PureScript or Coca regarding variants of records? That's a good question. This is like a different kind of design space. I have explored this before. I think that the using polymorphic records in order to build polymorphic variants, extensible records in order to build polymorphic variants is a viable approach, but it has trade-offs, and I think one of the trade-offs is that you have to handle all of the variants, and in the OCaml variant you can only handle like one thing and leave the rest, return them as is, for example. Maybe I have an example of this. Let's see. So, if I'm not mistaken, and I haven't looked at this in like a year, you can't really write this kind of code with extensible records, because you have to make sure you handle all of the cases, all of the variants. So I wanted to explore something else for my program, and it is always possible to implement them in userland. I have like a tweet that I made about this. Let me see if I can quickly fetch it. I think this is the one. My internet is failing me, but this is a different way that I like simulated polymorphic variants in GML with extensible records. I wonder if I had that here, that example. I think I don't. Maybe I should add it. Let's see if I can find it here. I really don't know why my internet is so slow, but it's not doing well today. I guess not. Not really working. Okay. In any case, I think this is enough for today. I should get some sleep. Thanks everyone for coming. This is like my first stream in like a year. I hope to try and do more of these. Let me know if you had fun, if there are other things that you would like me to talk about, or I will just continue working on my VM project and my programming language, and maybe have a look at GVCC, maybe look at get a deeper dive into compilers. Yeah, awesome. Thank you very much for coming. Really appreciate it. I had a lot of fun as well. Um, all right. Thank you, everyone. See you again.